Hi there, welcome to this week's video on quantitative analysis. As we get started, I want to just introduce you to the general concept for this lecture is to help you know when to apply which tests. We don't have much of an emphasis on how to calculate the tests because in the real world, most of the time you'll be using a statistical software to that. So today's lecture will generally be focused on helping you understand descriptive and inferential statistics from more of an applied perspective rather than a theoretical one, which you should have developed a good understanding of when taking 501 and 502. And so to begin, let's just refresh ourselves about the general difference between descriptive and inferential statistics. Descriptive statistics is generally focused on describing or summarizing data, describing what you see. So this includes if you're working with categorical data. I just realized on the slides these words are flipped. So it should read, for categorical data, use parametric or non-parametric or just the generally useful minimum maximum descriptors. And so parametric, meaning you kind of have a normal distribution, use a mean and a standard deviation when you have a continuous or numeric outcome. And then when you have a non-parametric data, which we will get into a little bit later on how that would be tested, you would use a median and interquartile range. Whereas for categorical data, again, I apologize for the slides being wrong as we're recording this video. I'll correct them before I post the slides themselves up to course spaces. But when you're working with categorical data, that's when you're using frequencies and proportions. Usually you're describing, the number and percent of people in each group of each level of your category. And so that's generally the distinction. Sometimes you might find if you're working with kind of both that you're going to use a mix of them. For example, you might report the mean and standard deviation for each level of a categorical data set, especially if your explanatory factor, which we'll explain on the next slide, is categorical and your outcome factor or your dependent variable is continuous or numeric. And so that's descriptive. Your mission is just to describe. And so we use those various statistics like the mean, the median, frequencies and proportions to describe. However, oftentimes you're interested in making inferences about the things you describe. For instance, if in one population you see, oh, well, the rate of cancer is 5% higher in this population, you want to infer as to whether or not that is meaningful. You want to draw a conclusion about what you found. And that's where inferential statistics comes into play. And so you have bivariable inferential statistics. That's when you're drawing an association between two variables. And so maybe you look at the association between coffee drinking and lung cancer. And you see, okay, there's an association or there's no association. That's just two variables. So you're using bivariable statistics. Well, there's really no reason for coffee to cause lung cancer. So you might think of, well, maybe there's a confounder. And the classic example is that, oh, people who drink coffee tend to be more likely to smoke, and that is actually what is causing the cancer. And so if you had a multivariable model, which means you were looking at the association between multiple variables, then you would be able to see, oh, when I include smoking, the effect of coffee is no longer significant. And so multivariable statistics is important when you think that you're going to have confounding effects in your model. That's important because as you describe your plans for your analyses and that sort of thing, if there are significant confounders that you haven't controlled for in the design of your study, either by using something like matching or randomization, then those things could potentially want to be paying attention to the potential confounding effect of those confounders. If you are using something like matching or restriction or some other design-based way to control for confounding like randomization, then you can worry a little bit less about multivariable approaches because the confounders should be randomized between the groups, or you should be matching based on those potential confounders in the design of your study. For this assignment, I'm not requiring you to use multivariable statistics. And in fact, we don't go into much depth in this course about multivariable statistics. You can say that if you are going to use multivariable statistics, that you would use either multivariable logistic regression if your outcome is a categorical variable. So that could be multinomial if it's a multi-level categorical variable, or binomial, which is if it's just two levels of a categorical variable. And then if your outcome is continuous, then you can just say you'll use a linear regression or that sort of model, a multivariable linear regression. So that's all the detail I really want you to go into. You should have enough of basis of an understanding to make that distinction from biostatistics. But really, the analysis plan that you're going to be covering this week, which you can see the instructions for this week's assignment on the slide now, will mostly be focusing around what bivariable tests are you going to do. And so that's meant to just make it a little bit easier. So you don't need to include too much attention to multivariable unless there's just really clearly an obvious confounder that you've left out of the design phase. But anyways, with regards to this week's assignment, basically, I want you to take your quantitative indicators. You can select a subset of those from your outcome indicator matrix or your impact matrix. But basically, I want you to select at least the ones that are most pertinent to how the decision maker using your data from your evaluation will use to make decisions about the programs. And so if you think that there's an important criteria that is going to influence the decision maker as to whether or not they want to continue or not continue your program, then you need to develop some sort of analysis plan for what's going to inform them to make that decision. And so those are the indicators that I want you to select from your outcome indicator matrix or your impact indicator matrix. And I want you to think of what are the tests you're going to use there. For your process indicators, this isn't usually as much of a concern. It's not always important that you have this sort of statistical rigor. It really tends to focus on the outcome indicator matrix when you're doing this sort of work. So again, for those quantitative outcome indicators, you're basically going to need to be able to identify the statistical test you're going to use, set up a decision rule and what your hypothesis is or what you expect to test, how you're going to test it, and then just explain what the decision rule will be. You know, if the p-value is less than 0.05, you'll reject the null hypothesis and assume the intervention did not result in a statistically significant improvement. So I put an example here of just of what your analysis plan might look like for a component. So if you're just doing one survey to assess all of your indicators, then it can be as short as this, where you say, you know, component 1 of this proposal, which consists of a baseline and a follow-up survey, see appendix 1, that's where I should be able to find your survey so I can look up what types of questions there are. Remember, you'll be handing in your survey assignment and this assignment at the same time. And so I should be able to go back and forth and look between them. But then I say we'll utilize a one group pre-test, post-test design. And so now I know just from that I'm going to be looking for paired tests, right? Because you're pairing your pre-test and your post-test. We'll get into paired tests a little bit basically after this slide. But I'm basically wanting to look for that. And the variables that are included in that example appendix, you know, is anxiety, depression scores, which are going to be measured at 6-month follow-ups using a paired sample Wilcoxon test. So that's how I'm going to test that one. And then another outcome is changes in self-reported substance abuse, yes or no, in the past 6 months will be assessed using a McNemar's test. And then a third outcome, changes in self-assessed physical health. You can see very good, good, poor, very poor, will be assessed using the Friedman test. And then for all those tests, we will use a standard cutoff determining statistical significance of the intervention. P 0.05 is pretty standard. If p-values are less than 0.05, we will assume the intervention had no statistically significant effect. Descriptive statistics for all variables will be calculated and reported for baseline and 6-month follow-up surveys. And so that's your analysis plan, just a short, succinct identifying, you know, these are my 3 outcome indicators that I'm interested in. They were HADS depression, HADS anxiety, substance use, yes or no, that's probably across a variety of substance use measures. Did you smoke? Did you drink? Did you use cocaine? Did you use meth? Each one that you're looking at, and then changes in a self-assessed measure of physical health. And so that's as simple as the assignment really needs to be. Just make sure that that you choose like kind of the right statistical tests in the right situation, that you lay out kind of an easy to follow. You see, I've done some things in writing this component one. I've identified that this is one specific thing. It's a follow-up survey. I tell you what sort of design it is so that I can use that information to pretty readily assess, yeah, McNamar's test is good there, Wilcoxon test is good there, and Friedman test is good there. So those sort of things need to be kind of laid out so that I can readily assess kind of in one paragraph or by looking at this paragraph in combination with your appendix assignment, whether or not you're using the right tests. And then the interpretations of the statistical tests need to be appropriate. So, so you can decide on what that means. If you want to use a higher p-value because you're completing lots and lots of tests, that's justified. You will have read about that in the chapter, the idea of kind of this multiple testing and the effect that that can have on the probability of observing a type 2 error. But yeah, and then so that'll be graded as the previous week's assignments are. So in doing that, there is this link here at the bottom, the guides.nyu.edu, which helps you choose tests. So I highly encourage you to use that resource. There is also a table 22 in the textbook, which has a breakdown. That doesn't provide nearly as much information as the NYU guide does. So I would suggest you look at the NYU guide to try to figure out, maybe consult between the two if you're having a bit of struggle. The table 22 in the textbook, I will note that it's slightly revised in the current edition that's posted to course spaces now. That's because I had switched a couple headers in the wrong direction. And so, so please re-download or reprint that one page that has table 22 on it. I also updated the link so it has this NYU guide link. It had an older link that I kind of found it wasn't as useful. I think it was still more difficult to use and even stumbled me a few times and I landed on the wrong test. And so don't use the old link that's there under the decision tree in the textbook. Use this new guides, nyu.edu/quant/choose test one dependent variable. And that should be a very hopefully useful tool for you. If you have questions on how to use it, if you're confused, post to the discussion board and we'll work that out together. So let's talk about how to use that tool by going over some important terminologies, that of independent and dependent variable. So an independent variable is the variables that you think explain an outcome, right? That sort of makes sense. They are independent of the outcome. Therefore, they're the things explaining it. So in an example, say looking at smoking and cancer, cancer would be the dependent variable because it depends on the independent variable. And smoking might be your independent variable because in a causal logic model, smoking would cause cancer. Cancer status would be therefore dependent on smoking status, at least in part, right? And so that's kind of the broad distinction between independent and dependent variable. It gets tricky in bivariable statistics because, oftentimes you're looking at something and the causal logic isn't entirely clear. And so in those cases, I would generally say health outcomes, the things you're measuring, those are your dependent variables. And then the comparisons you're trying to make, those would be your independent variables. And so groups, a treatment group versus a control group, for instance, that would be an independent variable. Time, pre-test versus post-test would be the independent variable. Whether or not they had the intervention, independent variable. Whereas dependent variable would be things like depression, anxieties, whatever the outcome is going to be. And so if your intervention is to reduce smoking, maybe your outcome is smoking, even though, yes, smoking is ultimately what causes maybe a health outcome that you're concerned with, cardiovascular disease, cancer, that sort of thing. And so generally dependent variable, again, is the thing that you're interested in testing whether there was a change in that thing. And the independent variable is the thing that you think logically what could have caused that change. So hopefully that's clear, because I think really that's one of the biggest requirements to do well on this assignment, is just being able to tell which is which so that I can choose the right test. And so let's talk through a few of those common tests. So if you've got two numeric variables, say you're looking at white blood cell count, and you're wondering, well, is that associated with number of cigarettes smoked in the past week? So you've got two numeric, both of them, blood cell count is a count of cells. Cigarettes is a number of cigarettes. Those are both kind of numeric count-based variables. And so you could use Pearson's correlation if your data are normal. Now, count data are not usually normal. Number of days in the hospital, those tend to have like something like either like a binomial or negative binomial, or a Poisson regression, Poisson, sorry, it's French, I guess. So yes, make sure to think that through. You don't need to specify. If in your analysis plan you say, we're not sure whether this is continuous, therefore we're going to do a test for we're not sure if it's normal, so we're going to do a test, and I'll give you a couple tests that you can use in the coming slides to decide if it's normal or not. So if it's normal, it's Pearson's correlation, and then if it's not normal, that's Spearman's rank or Kendall's rank. And then for if you're doing a numeric dependent variable, so again, something like number of cigarettes smoked, and a categorical independent variable, so like whether or not they participated in your intervention. So you're saying, if they participated in our intervention, did they smoke less cigarettes? And so to do that, you would use a student's t-test if the variances are equal. And so variance, remember variance from the textbook is kind of the distribution of number of cigarettes smoked. So maybe if the variance of the people who participated in your intervention is much wider or much narrower than the variance of people who didn't, then you want to use the Welch's t-test. And so the Welch's t-test is just an option for when the variances are not equal. There's also the issue of when your data is paired. If your data is paired, so your cases and controls are matched, you are doing either pre-post testing or you're comparing kind of natural pairs. In these situations, when there is some sort of reason that you need to connect specific individuals in your data set, then you use a paired t-test, and you can do that. If you've got a non-normal dependent variable, then it's Mann-Whitney test, and if it's a non-normal data, and the data is paired, then you would use a Wilcoxon signed rank test. And so the paired t-test can be replaced by the Wilcoxon signed rank test. The student's t-test can be replaced by the Mann-Whitney test, or the Welch test can be replaced by the Mann-Whitney test. I would say generally normality supersedes variances. And so if there's an issue with normality, use the non-parametric test. Welch's t-test is kind of proto non-parametric in that it still kind of has an assumption of normality. So the Mann-Whitney test is generally a more flexible test for you to use. So then if your outcome is numeric dependent variable and a categorical independent variable, in those cases, that's slightly different from this if you got more than two groups. So those previous examples were just two groups. But if you've got more than two groups, then you can use one-way ANOVA if your variances are equal. So one-way ANOVA replaces the student's t-test. Welch's one-way ANOVA if the variances are not equal, so replaces the Welch's t-test. And then if the dependent variable is non-normal and you have more than two groups, then that's the Kruskal-Wallis test. And so you can use that. So those tests are just basically there's more than two groups. So getting at this issue of whether or not something is normal and whether or not the variances are equal, the Shapiro-Wilks test is used to assess normality of a numeric dependent variable. The Levine test is used to test whether the variance of a numeric dependent variable is equal between two groups or the levels of an explanatory variable. So if your groups have an equal variance and the variable is normal, then you're using the parametric test. If they don't, then you're using non-parametric tests. So that's why there's all these test alternatives, like the students to the Mann-Whitney, or the Wilcoxon-signed ranks being an alternative for paired data. Those are basically non-parametric alternatives for those standard parametric tests. And so hopefully that should be somewhat of a bit of a refresher from 501 and 502. And then if you have two categorical variables, if your data are paired, then you can use the McNemar's test. If your data are not, you can use a chi-square or chi-square test or binomial logistic regression. I will say that logistic regression tends to be more flexible in general than the chi-square test, and you can calculate an odds ratio from the effect of logistic regression. And so that's generally quite useful because odds ratios, I think, are easily interpretable, at least more so oftentimes than the coefficients that come from regression. And then chi-square doesn't even really have an interpretation of the chi-square value. Simply the p-value tells you whether or not it's a significant difference. And so those tests are available to you in kind of the situation of two categorical variables. If you have a categorical dependent variable and a numeric independent variable, then you can use binomial logistic regression. And so you notice that binomial logistic regression was on the last slide as well. Well, that's because when it's the outcome, it's fairly tolerant to the binomial logistic regression. You can have an independent variable really of any type. And so that's important for when you think of like multivariable modeling. When you decide what to model, you decide what to model based on your outcome or your on your dependent variable. And then you can have any type of independent variable, whether it be numeric or categorical. And so hopefully that's clear. The next kind of situation is if, again, you have more than two groups, and instead of the binomial logistic regression, you have multinomial logistic regression. And again, that's based on more than two groups of your dependent variable. And so you can think of the differences as like, well, say I split my data, say something like annual income. If I split it above and below $30,000 a year, then that would be a binary binomial logistic regression, right? That would be the outcome. I would use logistic regression, but I'd use the binomial. The multinomial logistic regression would be if I had something like, say, let's use ethnicity, for example, right? There's maybe white, Asian, South Asian, African, Caribbean, and Black, East Asian, Arab, indigenous. You can think of any of the ethnicities. Those are all categories. And you could use that as an outcome in your model and say, what is associated with, ethnicity? So then you pick your variables. And in that sort of situation, because your outcome variable is being ethnicity, you would use that in a multinomial logistic regression. Now, of course, ethnicity is usually thought of as an independent variable. So another example of that might be, say you take a continuous blood cell count and you divide it into 4 groups, right? Really, the multinomial is just telling you there's more than 2 groups here and you want effect sizes for each group. And so multinomial logistic regression is for that sort of scenario. So that's kind of the brief overview of the content that I want you to be familiar with. Those are the main tests that you're likely to encounter. A lot of you are probably going to be relying on paired tests because either you're doing pre-post testing. You might also find that you need to be flexible in choosing which tests you do. If you're comparing 2 groups, for example, and you're comparing a pre-post test for both group, you need to think about how are you going to make that fit into the model. And so maybe you would calculate the difference between the pre-test and post-test score, right? And so maybe someone scores 32 on one, maybe the baseline, and then 28 on the other. Their score that you're going to be looking at is 4, right? Rather than having a 32 and a 38. And that way you compare, well, what is the average change in a person's score who was in the group versus the average change of a person's score who's out of the group. Now, there are statistical methods to analyze things like the Solomon 4-group study design and these other study designs that we think of. But I think the best thing to do is to keep it simple in this analysis. So just simply think, well, how can I make this indicator fit into one of these basic or common statistical approaches? And then hopefully you'll be able to figure out. However, if you do have a question this week, make sure you reach out to me on the discussion board. If you're looking at table 22 and looking at the NYU and you're like, oh, I still can't figure out which one I should be doing, just pose it to the question board. Either myself, Dr. Landy, or another student might have some insight for you. And so that's all for this week's lecture. Next week will be qualitative data collection. And then remember, your quantitative data analysis plan and your questionnaire is due October 27th, at the standard time, 11:55 p.m. or whatever. So with that, hope you have a good week and take care.